My name is Terry Mcann. This is a lovely little doodle that someone did for me. Very kind of them, thank you. So today we're going to be looking at talking about how we can deploy models faster, more reliable, more repeatable by using a bit of good old sort of standard development principles. So my name's Terry Mcann. If you want to find me on Twitter, you can do at SQL Shark. So I'm a Microsoft MVP, which basically just means I talk about a lot of Microsoft stuff, and I talk at events far too often, and I probably don't do enough work. And spent a whole week last week at various other events, and not done a great deal of work for a while. So I work for a company called Adatis. We're an advanced analytics consultancy. We specialize in analytics across the Microsoft stack and a whole load of other stacks as well. All right. If anybody wants to get hold of any of the slides, any of the demos, anything in here, there's probably about 4 or 5 hours worth of content on my GitHub for this particular session. You can find it if you search for SQL Shark on GitHub. You'll get it there. It's called Data Science DevOps. Okay, if anybody does have any questions as we're going, just stop me, just come shout them out. That's completely cool. Okay, so just a bit of, just out of interest, who is a data scientist? Who is doing data science at the moment? Okay, cool. Who's a software developer? Okay, a few more hands. Cool. Some crossover as well, that's good. Okay, so what are we going to do today? All right, we're going to try and do a couple of things. So in this session, I want to look to understand, what is a data scientist role, what they do particularly well, and what they also do, a bit bad. So we'll explore a bit of the history of DevOps. We'll look at the core components, and we'll look at, more importantly, how they're going to relate to machine learning. And then we'll look at how we can hook us all together with a couple of things such as Azure DevOps and Python, Docker, Kubernetes, so that we can get our models into production a lot quicker. Okay. So this quote came from a great book by O'Neill and Schultz, which is the productionization of machine learning is the toughest problem in data science. I think for a lot of people who are sort of getting into the field of machine learning and getting into data science, they probably think, what's the hardest thing I have to do? Well, I have to select the right appropriate algorithm for the problem I have. I need to tune it. I need to cleanse my data. I need to do all this sort of stuff. And yeah, those things are hard. But you'll quickly find one of the hardest things actually comes in, well, how do I deploy this code? Finding a machine learning engineer who can build you a model is difficult. Finding you a machine learning engineer who can build you a model and deploy that in a way that is both responsive, has good uptime, all these things that you want, that's when you're into the realms of the data science unicorns. Okay. So, why is it so hard? Why is the productionization of machine learning models just so difficult? So I think the first thing is, if we look at the range of languages, that we typically work with, you may be building a model in R, you may build that in Python, in Julia, in Scala, in any tool that you're particularly interested in. So there's a study recently compiled by MapR in a book by Ted Dunning and Ellen Friedman called Machine Learning Logistics. And they looked at their customers, and they asked their customers, okay, of all of the machine learning languages you use, how many languages do you have? How many languages are you using? Like, what are your teams actually doing? And on the smallest amount they had their teams using 5 different languages. On the larger companies, they were using 13 different languages. So that's between 5 and 13 different languages that we need to work with, that we need to be able to deploy, that we need to be able to get out there in any particular way. And one of the things that we get commonly asked as a consultancy is to go in and work with customers in whichever languages they currently use. So they may be really, really hot Python developers and maybe really good R developers, but what they struggle is how they can get that into production. And the other thing they do particularly as well is, when a company looks to try and hire a new team, they might take a whole load of graduates straight from university who come with a whole host of languages and a whole host of different things that may not be the norm for their businesses. There may be even new things that they're looking at. And getting that stuff into production in a reliable, repeatable way is a real problem for a lot of people. So what else? So let's look at our friendly data scientist here, and let's talk a bit about the skills and what they really do. So a lot of the customers we find typically take on teams, especially if they're new teams and they're not so familiar with the field, they'll rush ahead and they'll recruit a load of PhD graduates straight out of university who are very highly academic, and they're very statistically minded, they're very, very smart people. They are particularly strong in a lot of machine learning languages. However, they're probably not from a traditional software background. They spent a large amount of time in academia, not in industry. They know things like R and Python for machine learning very well, but they may not know how to actually deploy things. Talking about stuff like REST APIs and the like, and sort of just general software principles are seldom the sort of skill set we see for data scientists. I think testing is hard. Testing is hard. Testing is sort of completely seldom done by a lot of data scientists. They don't use source control. Everybody here using source control for everything they do? Yeah. Everyone whose hands didn't go up. If you take away one thing, it starts source controlling absolutely everything. I was working with a customer recently. We source control absolutely everything for them, apart from they had a small team who did one thing for us, and they didn't source control it. And of course, of everything that we lost that one thing, and someone had to rebuild it from scratch because it wasn't in source control. Source control, source control. Okay, the data scientist thinks that deployments are the responsibility of someone else. Now, and this is a bit of a mind shift, I think, for a lot of data scientists that people need to start realizing is a couple of years ago, it was probably okay to just be that guy who built machine learning models. But now you need to be that person that can build those models and deploy them. So how can we help? Just as a result of all of this stuff, the result and the outcome of this is that models just never make it into production. Models will typically just sit there on local machines, on laptops, on servers, and they'll be used across bits of batch data, but they typically will never make it into production. And what I mean by production may be in front of your business application. So maybe you have a website, and that website is selling something to your customers, and you want to know, okay, well, when's this person potentially going to churn? What can I do? Can I offer them an incentive to stay? Can I do something? So those models never quite make it to that point where they go actually in front of a customer. Or they may not make it into somewhere where it is classed as production and we don't want to change it. So models never really make it into production. Okay, so how do we fix this problem? So I think, based on the title here, it will be no surprise, one of the ways that we could fix this is by applying DevOps principles. Okay, so let's go back on a bit of a journey to the sort of mid-2000s. We've got our friendly chap here, our friendly moustachy friend here, who is our developer. Okay, and as a developer, I write a lot of my code in Python. Okay, I write new features, I fix old code, I fix bugs, but I wait weeks to deploy my code. I wait weeks, or maybe months. I wait a long amount of time to actually be able to get anything into production. And as a result of that, the time to market of our product is suffering. So we're not actually able to ship code fast enough. The code that we're doing has to just wait a long amount of time. And yeah, our product is suffering. The customers are not happy. And as a developer, I think this is the fault of operations. My role is to write the code. My role is to fix the code. And then I pass that off to operations, at which point it's their responsibility. And they're the reason that everything is too slow. Okay, so we have our operations guy. Notice our trendy developer and our old stuffy operations guy. It's never the way it works, of course. But from an operational point of view, so our operational guy, he manages the production code. But the difference here on the operation side is that production code is typically Java. It's not Python. So sometimes what happens is the code has to be rewritten. Sometimes they're happy with Python, but sometimes that means code has to be rewritten by operations, which is partly why things start getting slow. The developments aren't the same. Our dev environment is not the same as our production environment. They're not equal. So stuff that the devs are building, we're not putting onto the same hardware, we're not putting on the same kit. From an operational point of view, they're responsible for the uptime, for ensuring that our applications are running. They're not so interested, in the actual code, more interested in what it's actually doing and ensuring that it's, performing in the best way for customers. They manage hundreds of servers. So managing the code is one thing, but they manage the whole infrastructure as well. The company is growing fast, and so it's a responsibility to keep up with this stuff and just keep everything afloat. They own the bugs from deployments, and they find that developers just don't care about uptime. So on one side, we've got developers building in one language, we've got operations deploying in another. You've got guys who care about the performance of their code, but not necessarily about the whole uptime of their systems. On our dev side, you've got people who want to get code out faster, but our operations are worried about ensuring that 99.9% uptime. They can't handle something from the dev side going down that's going to impact the operational ability of their application. Okay, so how do we fix this? Oh, it's our lovely merriment. So what's currently happening is our developers are just chucking their code over the wall to operations, and it's like fire and forget, they're done, they're no longer interested. So to fix this, then we start combining things, dev and ops. So around about 2009, there was a conference which was to do with sort of, it was a software development conference. And at that time, there's a couple of people that met, and they met and sort of coined this term DevOps. What they wanted to do was to get away from this whole separation of duties and get closer to one single team, one interdisciplinary team who would be able to handle both elements. And so they proposed a whole load of various different things, but it can be broken down quite simply into sort of this list. So first things first with DevOps is a culture. So I think lots of people think when you look at DevOps, it's a tool set. But most of it and the bulk of it really comes from a culture, and it has to be a culture that's accepted across a business, across an entire team. So DevOps can't really be done in silos. It needs to be invested across your business. It needs buy-in from the operational team. It needs buy-in from the development team. Combining different roles from both works particularly well. So second is source control. So I think you could think of DevOps almost as a pyramid of what you need, and at that base is always source control. If you don't have controlled code, then you can't do the rest of the stuff that we want to talk about, and you don't have any guarantees that the code that you have is stored in a reliable way. So once we've got our nice code, it's all stored in a reliable way, then what we want to do is we want to do continuous integration and testing. So we want to say, okay, as I make a change to my code, I want that code to be tested. I want to be able to run unit tests. I want to be able to run integration tests. I want to ensure that every change I'm making in a way that is benefiting my product, and that I don't need to almost worry about testing, that I write a whole load of test plans, I write a whole test harness. What I do is I just commit my code to source control, and the rest of it works out. I want to talk about, I want to do continuous deployment. So if my code all checks, if my tests all work, I don't want that to be deployed. So I want to move away from having my devs and my operational team going from my, sometimes like half-yearly deployments up to deployments whenever I need it. Who uses Spotify, or uses the desktop version of Spotify? You'll typically see quite frequently is you'll start using Spotify and it will want you to close. It want you to close because there's been changes. And you can probably wait, 4 hours later, and it might suggest that it wants to close for changes again. That's because they're doing continuous deployment. Their code is continually deploying on such a high frequency that sometimes you can see that it wants to restart daily. I want to do infrastructure as code. So again, I want my hardware from my dev side to match my hardware on my production side. And I don't want there to be any configuration changes sort of between the two. I want to be able to write that as code, and I want to be able to source control that. If I decide that my application gets particularly big, it's getting a lot of traction, and I want to scale that out to a couple more machines behind a load balancer, I don't want to have to manually go and do that stuff. I want to know that I want to take code which describes how this all works, and I want to deploy it in a repeatable way. I want to do that so that it's all configured in the right way, and I want to automate as much as possible. And then I also want some operational monitoring and feedback. So that's what sort of DevOps has really helped with, accelerating traditional software development into production, sort of really minimizing those life cycles. There's a survey which comes out once a year from Puppet, and Puppet produce tools, and they do this DevOps survey every single year. And in the last couple of years, one of the things that they ask is, of your teams who have embraced DevOps, what's the general satisfaction amongst your teams? Are people happier? And they typically find by getting their code out there, their code is tested, and it's better, its route into production is a lot easier, that they have happier staff. They have a lot fewer errors, and their time to production has decreased massively. It takes hardly any time to get code into production. So that's sort of how it's worked for traditional software. But when we talk about machine learning, we're not necessarily building traditional software. So these things are a bit different. So when we talk about source control, we're not talking about source controlling, classes and code. We're talking about source controlling, the code of our particular model. But then we get onto interesting things like, okay, what do I do with my data? I can have a particular machine learning model, I can have all my code to train it, and that will get me a level of accuracy. Then I can improve that with just better data. I can improve that with a wider set of data. So I can improve on my model without ever making any change to my code, which is a really interesting thing for how you do DevOps. How do you source control data versus how do you source control your code? Continuous integration and testing. Well, how do you test a machine learning model? Can you test it so that you're getting a response back? What is testing? Does testing look like something like, what's the success of my data? Am I getting a level of accuracy that I'm happy with? Continuous deployment. So deployment, once we start moving machine learning models actually into production, we start getting into the realms of, well, how do you manage those models in production? From an operational point of view, the operational people are more concerned with, okay, well, what's the latency of that particular model? If I put a model in front of a customer in a customer-facing website, then that model needs to be returning in sort of sub 200 milliseconds. If that model is returning any slower, then that's going to make a slight dampener on what that person is seeing in the load time of their website. If they start seeing things slow down and they're not being able to use their site responsively enough, then they might move off to somebody else. If it's something like, if I'm selling you a product that loads of other people sell, and you can go somewhere else just as easily, and my machine learning model is slowing you down, what's to stop you just leaving and churning and going somewhere else? We don't want that to happen. So those sort of monitoring and uptime is really important. But then also, once machine learning models go into production, they immediately start to decay. And what I mean by decaying is if I train a model with 100,000 lines of data, then I see 200,000 lines of new data come in, then there's a good chance that what my model in production is no longer reflects reality. And there's a degree at which a model starts to decay, and how quickly that decay happens will entirely depend on what the problem is that you're trying to look at, and also how frequently your business changes. Let's say I build a recommendation engine. And when I build that recommendation engine, my company only sells stationery. So I sell pens, I sell pencils. And then through an acquisition, we buy a company that makes something like, planes. And we start selling planes. I imagine things like jet engines are slightly more expensive than pencils. And that completely warps what that model was trained to do. So that recommendation engine is going to start throwing out some crazy results. So that decay is entirely dependent on what you're trying to do. But from an operational point of view, they're going to be really interested in knowing what, the rate of that decay and if that actually is making an impact. Okay. So what I want to do for the rest of this is go through a couple of things which look to try and solve various different elements down this journey. So we're going to look first at a little bit of Python code. It's a very basic machine learning model. It's just going to do some regression. We're going to look at source controlling that code. We're then going to look at how we can wrap that up in a way that's going to be repeatable for various different environments. So one of the things a lot of my customers come to me with is problems around how can they guarantee that the data that they use and the code that they use to train a model would be repeatable. So if they try and do that again somewhere else and they try and get the same results back, how can they guarantee they'll do that? And that's massively different. That could fluctuate between what hardware it was run on, how much data they had. There's a whole load of things that could change. So we're going to look at how we could potentially make that a little bit easier with Docker. Then we need somewhere to deploy our Docker images, and then we need somewhere to run them. So this is our sort of flow here. Okay, right, cool. So let me zoom in a little bit. So what I have, zoom, view, zoom, it's fine, we'll do it this way. So what I have is a very basic model. What this model is trying to do is it's just using, so this is using Python, it's using sklearn, which is a machine learning library for Python. It's using an inbuilt data set which looks at some diabetes data. And it's looking to do a regression analysis over just one of those features, so just one column of data, and it's looking to try and predict based on the value what this other value is. But one of the first things that it's doing a bit different to sort of how I normally build something is there's a whole load of boilerplate stuff up here that I've used. So rather than just using sklearn, I've pulled in a few other things. So I've pulled in Flask. And what Flask will do is give me a very nice REST API on top of my model. So when I want to call this model, when I want to call this bit of code, what I'm doing is I'm exposing an API across the top. And so that way, whenever I want to get a response back, I can just ping a REST API and I can get that response back. I can secure that API in any way that I want to, but I'm guaranteeing that I should get a response back. And I think this is one of those shifts that sort of machine learning developers need to get away from is they should start thinking about how you're going to expose your model almost from the get-go. So I'm importing here Flask requests and JSONify. So I'm going to give a response back in a JSON format so that if I'm building an application that's going to consume from this, it can consume in a format that it knows, a format that's very easy to read. Then I'm going to use another library here, which is Pickle. Fantastically named library, Pickle. So what Pickle is going to look to do is to deserialize and serialize my model. So for anyone who's not a machine learning engineer, what I'm going to look to do is produce a model. I'm going to train that model. So I'm going to take a generic algorithm, such as a regression algorithm. I'm going to apply some data to it. I'm going to tweak a few parameters, and I'm going to output my sort of model. Now that's really cool if it just sits there, but what do I do with that model? I need to take that model and put it somewhere else so that I can start using it. So I'm going to take that model, I'm going to deserialize it, I'm going to serialize it, as bytecode, and I'm going to persist that bytecode somewhere. And then when I want to call this model, I'm going to deserialize that bytecode, and then I'm going to just call my model. So now the benefit of that serialization and deserialization process is that I can guarantee at that time of running, every time I call that model in the future, that I should be getting a repeatable result. I should be getting the same result back. It also means that I can version control the outputs of my models. If I produce version 1, and that's working particularly well, I get some new data, I've read some new journals, I've thought about some interesting ways I could improve this. If I retrain that model, I've then got version 2 of my model. I've got 2 serialized outputs, and then I can start saying, okay, well, for this new request, if I score you both against these, how different are my responses? Is this one performing better than this one? How do I handle that? So that sort of serialization process is really interesting and really important. Okay, so once I have here, the other thing I have in here, which maybe isn't the right thing to do, but in some circumstances may be okay, is I've separated this bit of code so it does both scoring and training. So if I can see what's happening, I can see my requests coming in, and I know how long it's going to take for my model to decay, then what I might want to do is just, based on a rate of decay, say, okay, well, actually, I'm going to retrain this data. And I can retrain it, re-pickle my model, and we're ready to go. Maybe what you want to do, it may not be. Okay, so that's a little bit of Python code. I mean, I can run that code locally. So if I just copy the path here and run. to run that one. Let's go for a different one. Right in the right place. So for anyone who's not seen this before, this is VS Code. VS Code is, if anyone's used Atom, VS Code is a nice rip-off of Atom. It's an IDE for a whole load of different languages, one of which is Python. You don't want to run. Why don't you want to run? No such thing. Okay, well, what this model would do is expose the REST API across my model and give me a response back. Now, what I want to do with this model is I want to take this model and I want to put it into a Docker container. And so by containerizing that model, what I'm doing is I'm trying to create an environment where my development environment is equal to my production environment. So what I want to do is, for my machine learning team, is I want to say to them, okay, well, if you're going to be using Python, what I want to guarantee is that when you build your Python model against a particular version of scikit-learn, when that goes into production, that we want to ensure that that version is the same as what the production version is. So what I can do is build out a sort of gold class production image that any of my team can use. So the way that sort of Docker works is, if you think about so sort of how software virtualization happened before, we'd have things like Hyper-V and virtualization and lots of virtual machines. And to produce a virtual machine, we'd have to include the hypervisor on the sort of base level, the operating system, all our code, all our libraries. And it was quite a huge undertaking to take all of that just to run your application and ship it in multiple places. When we're looking at a container, we're looking to strip away that hypervisor that gets run somewhere else. We're stripping away that operating system, and we're just taking the parts that we need. We're producing a more lightweight version of that. So what we're going to look to do is we're going to look to take the lightweight version, which will just be our code and our base image. Everything works from inheriting previous images, and we're going to look to take our code and push that off somewhere else. So Docker has a couple of different components. It has your sort of code, it has a Docker file, and then anything else that you might need. So here's an example of what my Docker file looks like for this particular model. So what we can see at the very top there is I'm inheriting from a base image. This one I'm just using Python 3, and this on-build image is an image that is kept in sync with the most recent versions of Python. To put this in production, I'd want to limit that down to a single version that I could guarantee is always going to be the same. And then saying, what I want you to do is copy me everything from my local directory, and then run me this command. So using Python, call my diabetes model Flask. And then that will get that running. So if I grab my README, and let's run that one. Cool. All my demos want to work today, which is awesome. Awesome. So that's helpful as well. So if that guy actually wanted to run, if Docker was actually deciding to run properly, what are you doing? So stuff is running, but you don't want to run. Okay. Oh, okay, you're already allocated for a different thing. Cool. So, so running this code inside my Docker container will guarantee that I should be able to get a repeatable environment from my dev to my production. And one of the other things that I can do in here is I can add in this requirements file. And so this sort of flavor of my Docker file makes an assumption that I've got a requirements file. And so this on build, what it will do is every time I try and run that, it's going to look for this requirements file. And then it's going to loop over each one of these and try and import the libraries that I need. So I can specify that I want pandas, scikit-learn, numpy, scipy, Flask, and Flask RESTful. But more importantly, I want Flask 0.12, and I want RESTful 0.35. So then if Flask 0.2 comes out, for example, and that's a lot farther ahead than what I've used to build this model, I can guarantee that this will still build on the model that I used, on the libraries that I used, and nothing else. For pandas, scikit-learn, numpy, and scipy, they would be with the most recent releases. Okay, so once I've got that, once I've got my model all ready to go, I need somewhere that I can actually run this. So one way that we can do that is using a tool such as Kubernetes. What Kubernetes will do is it will take a Docker container and it will deploy it for you and give you a nice API that you can call. So I could do that, but what I want to do is I want to show you sort of how that looks and how you can structure this stuff all together. So one of the things that I mentioned is there's a GitHub repo for all this stuff. So deploy models faster with DevOps. There's a whole load of things in here that you can go through, all of these examples, and touch wood, they will work. But I want to switch gears and start looking at a tool called Azure DevOps. So Azure DevOps is a sort of, if anybody uses Jira, if anybody uses sort of task management tools, Azure DevOps is a task management tool, but it's also a DevOps tool. So it will handle things like source control for you. It's backed by Git. It will handle your build pipelines, your deployment pipelines. It will handle any tasks you have, any bugs, integration tests. It does a whole load of various different things. So under this project, I've got a couple of build pipelines. And one of those is to take a model and put it in production. So what I want to do is every time I make some changes to my code in Git, I want that to be tested. I want that code to be packaged up into an image in Docker. I want that image to be deployed to Azure Container Registry. So what Azure Container Registry is it's a private repository for all of your images. So you might build a whole load of images, a gold class image for Python, a gold class image for R, one for Spark, one for anything else, any languages that you're looking at. And there are lots of public places that you can put those. If you want somewhere private, Azure Container Registry is a good one for putting those privately. So what I wanted to do is build that image, and I want it to be deployed to Container Registry. So for Kubernetes to work, there needs to be an image in a container registry somewhere that it can pick up and deploy. So what I've got here is a pipeline, and if I hit edit, we can see the steps here that it's going to do. So every time I make a commit to my branch in Git against my master commit, against my master branch, is going to do a few steps. So anybody who doesn't source control, if you're using something like Git, Bitbucket, any of the sort of GitHub, any of the major ones, you have a concept of branching. You'll always have a master branch, and then of that you can have multiple different branches. So maybe a master branch, a dev branch, you may have feature branches, you may have smaller branches, and your code will just go slowly back up. So by the time it hits master, you may alternately have a release branch. At the time it hits there, I know it's good, and I want that to go into production. So what this is going to do is it's going to monitor my master branch, and it's going to monitor for any commits against it. So if I make a change to any of this code, and I commit that, it's going to trigger this process. So the first thing it does is it goes away and it grabs all of my code. And the benefit of using a tool like Azure DevOps is that it's not going to run on a piece of, you can run it on your own hardware, but what it uses is it uses a cluster of machines in the cloud, and it just latches onto one of them, will download all of your code securely, build out everything you need to do, deploy it, and then it will delete all the code. So that gets on to an interesting thing around source controlling your machine learning models, which is never source control your data. Because if you start source controlling your data, your repository is going to get huge. If you source control your data, commit it, and then try to delete it, you can delete it from your local repository, But the beauty of things like Git is it will version control all of your data in there, and it will always keep it. So every time you go to download everything, it's going to download. It's going to still download it. It's going to take a long amount of time. So don't source control data. OK, so we're going to look to do a couple of things here. Who's using Azure currently, just out of interest? OK, hardly any hands. Cool. So Azure is Microsoft's cloud platform. It works very much like AWS, like Google. I've got a resource group here which contains a couple of different things. It contains a repository here for all of my images, and it contains Kubernetes as a service. So Kubernetes, as I say, is a fantastic way to take those models and deploy them, take those Docker containers and deploy them. It's quite hard to run on your own kit. By all means, not impossible. It's tricky to configure. This is a Kubernetes service. This is almost a managed service, a platform as a service offering of Kubernetes. You just get a name that you deploy your stuff to. You handle the scaling and everything else associated with it automatically. So if I quickly look at my container registry, what I've done already is I've deployed an image here. So you should be able to see here, I've deployed this guy, diabetes and version 1. And under version 1 is a manifest file which will explain how it should go about actually building this model out, everything that it needs. So then what Kubernetes needs is a little bit of YAML. And YAML is, if you haven't looked at YAML before, YAML is almost a prettier version of JSON. If JSON was a prettier version of XML, I don't know what will be the prettier version of YAML, but I'm sure in 2 years' time we'll find out. So it's taking this YAML manifest file, which is saying a couple of things. OK, well, where am I going to get that model? I'm going to go over here to this container. I'm going to pull that down. I'm going to expose it on port 571, and then I'm going to deploy it. So these steps in Azure DevOps. First thing we're saying here is go away, get all my code. Then build me that image. Then push that image to the container registry. Delete any version that's there. Kubernetes has a function called apply, and that will take your changes and they will just migrate those changes. It'll do an upsert of your code. Alternatively, you can just delete everything and redeploy it. And then that will actually deploy that code. It takes a bit of time, so I can have a quick look at one that's run before. Let's have a look. So what this is doing, what it would do if I was running it, it will go away to an agent. It's going to go and find a VM, download all of the code, start initializing everything. It's going to then download all of the data that it needs. So you get a whole load of stuff here. There's a whole load of different VMs that you can use for this. You can use a Linux VM. You could use a Windows VM. If you've got some dependencies on another application, you can use multiples. You can run your own. It's going to go away, get all that code. It's then going to build that image. So you might be able to see here. Step 1 of 3 is to go and get that image. Then it's going to go and create everything that it needs. It's then going to download everything else that it needs. It's going to pull in all the libraries that we want. It's going to get that image ready, and it's going to push it off to the container registry. Then it's going to push that image up. And then Kubernetes is going to delete that image, and then it's going to put that image live. So I did this earlier, and this is a Kubernetes dashboard. So what this is showing me is a couple of health statistics around my particular model. I've got my CPU usage, my memory usage. I can do some basic things in here, sort of see what's happening. I can scale if I need to. But I have deployed a model down here called production diabetes. And I can see, so the smallest unit of work in Kubernetes is a pod. In Docker, that's a container. In Kubernetes, that's a pod. You scale out based on pods. So Kubernetes sort of has nodes, and of those nodes, you can have multiple pods. It all sits behind a load balancer, and so your requests come in, they'll go to one of those pods. If none of those pods fails, if they die, if for some reason something in your model just completely shuts down, it will self-heal and spin you up a new version of it. If your model starts getting a lot more popular and you need to sit that behind a load balancer, then you can just add more and more and more pods. If you need more power, you can add more nodes with more pods and just scale out as you need to. Okay. So this is what you should have seen before, which is, so what's happened here is I've deployed that model, and so Kubernetes has exposed for me, if I have a look in here. So it's saying down here I've got a service running in Kubernetes called Production Diabetes. It's got its own internal cluster IP. So this is what it manages itself. So as things sort of come on, as those pods die, I'm never talking to the IP of the pod down here. I'm talking to the IP of the service. So if that pod dies and it's replaced by a new one, I don't need to repoint all my code. I'm just pointing it at my exposed service, which is currently running on this guy here, on this IP address. So if I point to that IP address, I can do things such as I can run my train. So what that train is now doing is it's reading in my data, and it's producing a serialized version. It's telling me that that model has been retrained. I should run score now. And if I run score and pass in something different. So this is now taking that serialized version from a Docker image, and then it's going to give me a response back. So now if I wanted to make a change to any code, I could go back to my code, make a change, as long as I was happy with it, run a couple of tests against it, hopefully through an integration test, and then commit that to my master branch, and then everything will go through to the point that it's rendered here. Cool. So I guess what we're trying to do there is this sort of flow. So that is somebody's building out a model. They commit that model into some kind of Git, be that using VSTS, which is what Azure DevOps is, or GitHub or somewhere else. That project gets built. That then gets compiled into a Docker image. It gets pushed into a container registry. That gets picked up by the registry for Kubernetes and then gets deployed. And then we have a REST API across our model. Any changes that we make to it, anybody we want to get testing it, they've got an API that they can call. Okay, I'd say if anybody wants to know anything more about this, I've got a blog series on various different aspects of applying DevOps to data science, with a whole load of different examples. There's an awful lot of content to try and cram into this session, but I'm also doing a full-day session on Wednesday, which is every element of this, but a lot more stretched out. So introduction to DevOps, Kubernetes, and then actually doing a deployment across the entire board. Okay, so I'll end on saying that DevOps will make your life easier. Start learning how to get your models into production. I had a customer of mine who did a whole project with us. He learned a whole load of stuff for DevOps, how to automate getting their models into production. He left the company that he was at, went to another company, and he doubled his salary, pretty much because he could take models from their concept straight into production. And there were not many other people who could do that. So DevOps will reduce your time to production, control and test your code, but monitor and manage those models in production. So there's a few more of my details there. As I say, SQL Shark on Twitter, tpm@adatus if you do want to email me, and then there's a few work ones as well. So thank you very much for your time today. If anyone has any questions, please shout.